In this video, I'll be talking about the mole ratio, which is the first concept in a series of videos about stoichiometry. So the first thing I'm going to do is a little bit of a review. So I talk here about the law of conservation of matter, which says that matter can't be created, nor can it be destroyed. All right, and that was important in previous units because of the concept of balancing chemical equations. We had the same number of atoms of each element on both the products and the reactant side of the reaction because of the law of conservation of matter. All right, and so when you're looking at a balanced chemical equation, such as this one down here, which we'll balance right now, the thing that gives you the relative number of molecules in this reaction is the coefficients on the reactants and the products. All right, so what this one says is we have 3 molecules of H2, and that reacts with 1 molecule of N2 and 2 molecules of NH3. Now, as a bit of a thought experiment, I want you to imagine what would happen if we had 3 dozen molecules of H2. All right, 3 dozen, which is 36. Okay, 3 dozen molecules of H2. How many molecules of N2 would you need? Hopefully you come up with 1 dozen, all right? If we have 3 dozen molecules of H2, it would react with 1 dozen molecules of N2, and it would produce 2 dozen molecules of NH3. If we combine this with our idea of the mole from the previous unit, if you had 3 moles of molecules of H2, then it would react with 1 mole of molecules of N2, and it would create 2 moles of molecules of NH3. All right, and so what we see here is that the coefficients give us a ratio between the number of molecules that are involved in a chemical reaction and also the number of moles of molecules that are involved in the chemical reaction. So what we're going to do is we're going to use that mole ratio, in this case that 3:1:2 ratio, as a conversion factor between the moles of one substance to the moles of another substance. And so you can see here, I gave you as the example, we've got H2 to N2 to NH3 is a 3:1:2 ratio. If you use that ratio and you think if we have 6 moles of H2, that's double what is listed in the ratio. So we had 6 moles of H2, that's double. Then we would have 2 moles of N2, and also we would have 4 moles of NH3. All right, if we had 9 moles of H2, that is 3 times what we had in the original. All right, we're going to have a 9:3:6 ratio here. All right, which is the same as a 3:1:2. So 9 moles of H2 means that you have 3 moles of N2. All right, and it means that you have 6 moles of NH3. All right, we keep that ratio. And so this says, as a conversion problem, here's how you can think of it. For every 3 moles of H2 that you have, you can use as a conversion factor that you have 1 mole of N2. All right, and for every 3 moles of H2 that you have, we also know that you have 2 moles of NH3. And you could actually create a whole assortment of different conversion factors between the different substances in this chemical reaction, and it's all based on the coefficients that they have, that 3 and 1 and 2, in terms of the mole-to-mole ratio. And so I'm going to go through a couple examples of this process and show you how to use that ratio. So the first one here says, imagine that you had 5 moles of H2. How many moles of N2 would you need? So what we do, as in all of the other previous conversion problems, we start with the number that's given in the problem. We have 5.0 moles of H2. That's what we're given, moles of H2. All right, then we want to get out of moles of H2, and we want to get into moles of N2. All right, and so what we have to do is we have to look at this ratio. We said 3 moles of H2, 1 mole of N2, 2 moles of NH3. So 3 moles H2, 1 mole N2. we have 2 sig figs from 5.0 moles, and then the mole ratio itself, that 1 and the 3, those are perfect numbers. Those are perfect mathematical ratios. It's a 1 to 3 ratio, and so when we have that situation, that's one of those infinitely many sig figs sort of situations where we won't count the 1 and the 3 when we're counting for sig figs because it's a perfect number 1 and a perfect number 3. So 5.0 is what we're looking at. We had 2 sig figs to start with, so we're going to end up having 2 sig figs in the end. That is 1.7 moles of N2. Okay, now it says, how many moles of NH3 would you produce? And so we're going to start at the same place, 5.0 moles of H2. And this time we're going to go from moles of H2 to moles of NH3. Again, looking at the coefficients up here in this balanced chemical equation, we know that there are 3 moles of H2 for every 2 moles of NH3 that are produced. All right, so we have 3 moles of H2 for every 2 moles of NH3. So now we end up with 5 times 2 divided by 3. All right, that 5.0 has 2 sig figs. The mole ratio is infinitely many, so we end up with 2 sig figs in our answer again, and it gives us 3.3 moles of NH3. All right, continuing on with this same reaction, it says, let's say that we had 23.24 moles of NH3. How many moles of N2 would you need? All right, so now we're going to start 23.24 moles of NH3. Okay, and so we want to cancel out moles of NH3, so we put those on the bottom. And what we're trying to get is how many moles of N2 we need. So again, we're looking at NH3 and N2, so you go back up and look at this balanced chemical equation. NH3 has a coefficient of 2, N2 has a coefficient of 1. So it is a 2 to 1 ratio. 4 sig figs in our answer, and so we get 11.62 moles of N2. Okay, so now I'm going to go through and do the rest of the problems on this assignment. Make sure that you know how to go about balancing chemical equations. If you're confused about that, I have a previous video which is all about balancing. I recommend that you go back and watch that. But otherwise, I'm pretty much just going to go ahead and balance the equations for you. So on this one, if you have a 2 and a 2 there, and then a 3 in front of the O2, that creates a balanced chemical equation. And so this first one says how many moles of oxygen are produced if you have the decomposition of 6.59 moles of potassium chlorate. So we're starting with 6.59 moles of potassium chlorate. That's that KClO3. Okay, and then we're going to try and get out of moles of potassium chlorate and into moles of oxygen. If you look at the ratio here, basically the coefficients in that balanced equation are what go in front of here. So in front of KClO3, up in the balanced equation, we have a 2. So we know there's 2 moles of KClO3 for every 3 moles of O2 because there was a 3 in front of the O2 in the balanced chemical equation. So whatever's in front of it in the balanced chemical equation, that's what's in front of it in the conversion table when we're talking about that mole ratio. So you multiply those out and you get 9.89 moles of O2. 3 sig figs on this one. For number 2, again, we need to start by balancing it. It's actually the same one that we were looking at before, so we just need a 3 here and a 2 there. And it says if you have 0.0024 moles of nitrogen, 0.0024 moles of nitrogen, it asks how many moles of hydrogen are needed. So we know we're going to get out of moles of nitrogen and get into moles of hydrogen. Okay. It is 1 mole of nitrogen for every 3 moles of hydrogen that we have. And if you calculate that, 2 sig figs in our answer, we get 0.0072 moles of H2. Number 3 says, how many moles of hydrogen are produced from the following reaction if 9.06 moles of zinc are reacted with excess hydrogen chloride, or hydrochloric acid? So in this one, pretty simple to balance it. You just put a 2 there in front of the HCl. And then we're starting with 9.06 moles of zinc. The excess hydrochloric acid is just indicating that we have enough hydrochloric acid to react with all of the zinc. All right, so you can kind of ignore that in terms of the actual process for solving the problem. Okay, it just means that we have enough hydrochloric acid. So 9.06 moles of zinc, and then we're getting out of moles of zinc, and we're trying to get into moles of hydrogen. All right, and if you look here, that is a 1-to-1 ratio. All right. So what's interesting about this problem is we end up with 9.06 moles of H2 because it was a 1-to-1 ratio. So whatever number of moles of zinc that we had, we're going to have the same number of moles of H2. For problem number 4, balancing it, usually this is a combustion reaction. Usually with combustion reactions, what I do is I balance the carbons first. So I put a 3 here. Then I balance the hydrogens. There's 8 hydrogens on the reactant side, so I put a 4 here to get 8 hydrogens on the product side. And then I count oxygens on the product side. We have a total of 10. That's 6 from the carbon dioxide and 4 from the water. And so then I put a 5 here in front of the O2, and we've got 10 oxygens on each side, and that is balanced. Okay, so this one says that you have 2,400 point moles of propane. And so the significance of that point here, this 2,400 point, is it's a decimal point, and it says that those trailing zeros on the 2,400 matter. All right, so there are 4 sig figs in that. 2,400 moles of methane, propane, sorry, moles of propane. So moles of C3H8. All right, then we know that we're going to try and get rid of moles of C3H8. And it's asking us to get moles of oxygen, so we're going to try and get into moles of O2. On this one, for every 1 mole, because it's got a coefficient of 1 on C3H8, there are 5 moles of oxygen. Go through and multiply that, and you get 12,000. All right, now the interesting thing on this, again, if you look at our original number, it had 4 sig figs. This looks like it has 2 right now. If we put a decimal point on the end of it, it would have 5. And so we need to use that over bar to indicate that those first 2 zeros are significant, but the last one is not. All right, and so we have 12,000 moles of O2. All right, and on for this last problem. It says, how many moles of potassium nitrate are produced when 4.5 moles of potassium phosphate react with 4.5 moles of aluminum nitrate? So this one, balancing it, again, not too bad. We just have to put a 3 there. It says we're starting with 4.5 moles of potassium phosphate and 4.5 moles of aluminum nitrate. Now, that's a little bit confusing, but if you notice here, we have a 1-to-1 ratio for potassium phosphate and aluminum nitrate, and so that means we need the same number of moles of each. It says we have 4.5 moles of each, and so what that's actually saying here is that we have exactly the right amount, so that 4.5 moles of potassium phosphate or 4.5 moles of aluminum nitrate will react. Okay, so we can use either one of these 4.5 as a starting point in this problem. I'm going to use 4.5 moles of K3PO4, mostly because it's slightly shorter to write. All right, so then we need to get out of moles of K3PO4, and it's asking for moles of potassium nitrate, which is KNO3. All right, looking at the coefficients, there is 1 mole of K3PO4 for every 3 moles of KNO3. All right, again, if it's in front of the number in the balanced chemical equation, if it's in front of the substance, it's in front of it in that mole ratio, so we're just looking at coefficients there. All right, and we end up with 4.5 times 3 divided by 1, 2 sig figs in our answer, so we get 14 moles of KNO3.